Here's a half-tapped primary coil driving a large ZVS Tesla coil at 40 volts, 2 amps, producing a lot of wireless power from both ends at about 435 kilohertz. Be careful, a lot of power. Let's see how that works. Today we will be testing a half-tapped primary coil for a large ZVS Tesla coil. Now what do I mean? This is a large ZVS Tesla coil with 1,000 turns in the secondary. Now what do I mean by half-tap primary? I mean halfway up this long primary coil we have this yellow junction here where we feed the DC power in from this power supply through this little choke halfway up. So as the circuit oscillates, it can either go that way or that way alternately very fast at kilohertz frequencies. Now in a normal Tesla coil you just tap on the top and the bottom, the whole thing, but this one we're tapping in the middle. So we're just going to look at the properties of that and see what happens. Okay, now let's look at the circuit we're going to use to test this half-tapped primary coil on a 1,000 turn large secondary Tesla coil. We're going to use a standard 0 volt switching or ZVS circuit, and the schematic is given here. You have two MOSFETs here, and those are those two MOSFETs. We have two fast diodes, one here and one here, and that's that fast diode and that fast diode over here. We have a choke to stop too much energy from coming in. That's that choke over here, and so on. There's all these little circuits here, like a Zener diode, a 10K diode, a Zener diode, and a 10K diode. Some circuits have a capacitor across the coil. We tried it, it doesn't really help, it doesn't work. For a ferrite coil, you need that. And here's your half-tap primary coil here, tapped halfway up where the arrow shows. It's right there. Now the first major question is, how many turns do we need in the primary coil above and below the yellow tap point? There's our yellow tap point. Just by trial and error, I found that 4 plus 4 turns won't work. 7 plus 7 turns work at 20 volts DC in. 14 plus 14s work at 40 volts DC in. This was the 4 plus 4, where you have about 8 turns, and you could just tap in the middle here to get 3 or 4 turns above and below, and it just does not work in this system. Okay, let's look at 14 plus 14 turns first, up to about 40 or 50 volts DC in. That's this coil we have up here right now. 14 plus 14 turns of soft refrigerator wire tapped in the middle at this yellow point. Now when we turn the DC power up over here to about 10 volts, we can already see about not much oscillation coming through the multimeter. Let's go a bit higher. Come to about 20 volts. And now we can see about 1.6 megahertz coming through the multimeter, but we don't have much electricity coming out the two sides. Let's go to 30 volts. We still don't see any light in the bulbs. We've still got about 1.6 kilohertz coming through the multimeter. Let's go to 40 volts. And now we see the light bulbs all switch on, like that. Hot. Put a lot of power. Just about burned the shit out of me. So we got 433 kilohertz coming out of this big system. And it's very, very powerful. Use some safety precautions. Look at that. Okay, now for the next stage of this experiment, let's look at a half-tapped primary coil with 7 plus 7 turns up to about 20 or 30 volts DC. We had 14 plus 14 turns before, but now I've stretched it out. We should have 7 above and 7 below this yellow tap point. So the current either go up that way or down that way. We can put some power from this power supply and see what happens. Now when we add power to this 7+7 primary coil, go to about 10 volts, nothing turns on yet. We have only about almost no oscillation at 10 volts. We have to go up to about 20 volts, nothing's turning on. Not very responsive. And finally at about 27 volts, it turns on 2 amps. Not bad power. That's a 7+7 primary coil tapped in the middle. We have 481 kilohertz. Now that's okay. However, there's a trick to make it go a little lower voltage. Let's watch that now. Okay, now there's a trick to make this 7+7 half-tap primary coil oscillate low voltages. We just take a 10 nanofarad capacitor rated for high voltage and put one end at the top of the coil, the other end at the bottom of the coil, and here's your half-tap point. Now as I turn on the voltage now, get to about 10 volts, it's not on yet, but we are getting at 10 volts, we are getting frequency like we did before, 440 kilohertz. The light hasn't come on yet. And as we go into about 15 volts, the light comes on weakly. It wouldn't come on before, and we're still at 450 kilohertz. And we go to 20 volts, that comes on quite nicely, 25 volts, 30 volts. So at 30 volts it comes on quite nicely, 460 kilohertz. Don't touch it or I'll burn. We get quite a lot of power out of it. Today, to summarize, we've used 2 MOSFETs and 0 volt switching with 2 fast diodes to create wireless energy at 500 to 1000 kilohertz frequencies. They're the 2 MOSFETs, 2 fast diodes here and here, and we're getting wireless energy in and out of the top of this long coil. And you see it's half tapped in the middle, 7 turns up, 7 turns down, alternating, and there's the tap point for 26 volts. We get a lot of wireless energy. So that works. Now it might also be interesting to test self-tap primary coils for a large Tesla coil when using 555 timers or air gap circuits. And that's another experiment. However, for this experiment, we just want to see how the half-tap version works when we use a 1000 turn secondary coil and 7 or 14 turns up or down on a primary coil. Thank you very much. We can continue our efforts to learn more and more about electricity.